Dear students, welcome back to another session of operating system lecture video sessions. Today's topic is synchronization. It comes under Unit 2, Chapter 6. Let us start with the synchronization. So in this synchronization chapter, we are going to discuss about what is the background of synchronization, critical section, what is critical section problem, before that what is critical section, then what is the Peterson suggested solution, and how to synchronize the hardware, mutex locks, semaphores, and the classical problem of synchronization. At the last, we are going to discuss about monitors. So these are the objectives or topics we are going to discuss in Chapter 6, synchronization. Objective is to present the concept of process synchronization, to introduce the critical section problem whose solution can be used to ensure the consistency of shared data, to present both software and hardware solutions of the critical section problem. And we are also going to examine several classical process synchronization problems. So upon ending of this lecture video, you can be able to understand what is critical section, what is synchronization problems. In the next video lecture, we are going to discuss about Peterson's solution and the different solution. In between, we are also going to know about race condition. Coming to background, the actual background of this synchronization is the process can execute concurrently. You know what is process? There are different process will be in your operating system. So process will execute concurrently. That we already know it. We have studied, and we have already studied process scheduling algorithms. So the problem with this is this concurrent process may be interrupted at any time, sometimes partially or completely. When you are executing a particular process, it may be stopped. So that is the problem. So concurrent access to shared data may result in data inconsistency. For example, you are trying to print. And you have given 100 pages of print. So for the printing software have to work. That is, the drivers have to work, and your printer have to work. It have to check the sensors by using sensors, how much pages are inside. So there are several processes running for this printing process. So sometimes if the sensors are not working perfectly or the driver manager is not working properly, then the effect will be fall onto the other process also. The shared data may result in data inconsistency. That is a problem. So maintaining data consistency requires mechanism to ensure orderly execution of cooperating process. So that is the reason there must be a synchronization, or there must be a cooperation between a process to another process. So if we see an example illustration of the problem, so suppose that we wanted to provide a solution to the consumer producer problem, which we have already discussed in the previous chapters, consumer producer problem, that fills all the buffers. We can do by having an integer counter that keeps track of numbers of full buffers. Initially, counter will be set to 0, as we have discussed with the help of a C program, and it will be incremented by the producer after it produces a new buffer, and is decremented by the consumer after it consumes a buffer. So there must be a synchronization or a cooperation between the producer process and consumer process. That is more and more important. That is what we are going to study about. We take this producer. While true, that means there it is actually when you are going to produce an item in the next produced, every time initially counter will be set to 0. Counter is equals to 0. If counter is equals to buffer size, that means consumer not consumed anything. It is Producer has produced till the buffer size reached whatever the size he is having, the entire size will filled with the item, right? So if the counter is equals to buffer size, initially counter is equals 0. When it reaches to buffer size, then you should not do anything. That means it should not produce anything else. If counter is less than buffer size, then what you have to do? Buffer of in, that means the size of, for example, if the buffer size is 10, in will start from 0, 0, 1, 2, 3, 4, and so on. Then this buffer size, if it is already third position, buffer size will be at third. In third position, it is going to produce something, and next to produce will be stored in buffer of 3. Then this buffer size will be incremented with the help of modulo division. Why we have to use a modulo division at the time of linked list, circular linked list, we have studied that how to update a value from one place to another place, how we can move, because if it reaches the maximum value, for example, it's 0, 1, 2, 3, 4, 5, 6, 7. If we use the modulo division in plus 1, then it will come exactly whenever it reaches the top position, then it will come to back to the 0 position. Then you are incrementing the counter. Initially, counter is equals to 0. Now you are incrementing the counter. So this is the code for the producer side. When you are going to consumer side, so in the consumers also it is same while true. That means your consumer is ready to use the consumer. Right. So while counter is equal 0, that means counter is equals to 0 and counter is initially it is 0. Counter is equal to 0 means there is nothing to consume. There is nothing to consume. So do nothing. Next else, that means if counter is greater than 1, that means counter is, for example, somewhere at 3, then what you have to do? Next consumed is equals to buffer out. Previously it is buffer in, now it is buffer out, where you are storing that next consumed you are storing. Then out is equals to out plus 1 and buffer size. So out value will be incremented and counter you are going to decrement. Counter you are going to decrement, and that particular item will be consumed. Whatever the item here it is, that will be consumed, right? So this is about consumer side code. So it consumes the item in next consumed, right? This consumer counter will be minus minus, that is counter value will be reduced, and then the item will be consumed. So this will shows you the synchronization or communication between producer and consumer. If the consumer consumes, then only producer have to produce, right? So one more thing we have to know about is a race condition. A race condition is a situation that may occur inside a critical section. So this happens when the result of multiple thread execution in a critical section differs according to the order in which the threads execute. Race condition in critical sections can be avoided if the critical section is treated as an atomic instruction. There only it will be avoided. Also, proper threading synchronization using locks or atomic variables can prevent the race condition. So we have to prevent the race condition, right? So in the race condition, if you see here, counter plus plus could be implemented as how it will be implemented. So the counter value will be stored in register 1. So there is a register called R1, and register 1 is equals to register 1 plus 1. That is, you are automatically increasing its value and you are storing in the same. Now, this register 1 is stored in the counter. So actually, initially it was stored in R1, then after this is the first step, this is the second step, and this is again the register 1 is stored in the counter. So how you are going to implement this counter minus minus? So there is a register 2 and counter. So counter value will be stored in register 2, then register 2 will be decremented once, right? And then this value will be stored in the counter. This is the first step, second step, and third step. So this is the incrementation and decrementation part of your counter. Now, see this example. Consider this execution interleaving with count is equals to 5 initially. Count is equals to 5. So here you can see producer executes. Register 1 is equals to counter. That is, this is producer. Producer, what he is doing? Counter value he is storing in register 1. That is, count value is equals to 5. Then register value is equals to 5. Then producer executes register incrementation. Then register is equals to 6. Then consumer, what the consumer is doing? Consumer is also storing the counter value. But what is the value of counter? It is 5 only. Then register 2 contains, register 2 is decremented. So 5 value is getting decremented, that is 4. Now the counter is equals to register 1. What you are doing? Counter register 1 value is transferred to counter. So this is executed by the producer. Then consumer, what he is going to execute? Counter is equals register 2. Register 2 is having the value of 4. Now the counter is having 6 and counter from the consumer is having 4. So this is the problem. See, counter must be same. In the producer side, counter will be increased. Consumer side, counter will be decreased. But when you are doing such a kind of executions, producer, consumer, see here. S0 is producer, and then consumer and consumer. Then again you are giving chance to the producer, then consumer process. So when you are giving the simultaneous producer consumer chances, then that is leading to the race condition problem. That is, you are not having the counter value perfect. So this will become the problem. That is the reason what we are saying, race condition in critical section can be avoided if the critical section is treated as an atomic instruction. Proper thread synchronization using locks or atomic variables can prevent the race condition. Right? So this is about race condition. Right? Critical section problem. So critical section means when you are entering into the CPU and your process is entering into the CPU and it is utilizing the CPU. That particular part is called as critical section. So when you are giving the critical section, there must be several problems. What kind of problems we will face, that we are going to discuss here. Consider a system is having n processes, that is P0, P1, P3 and so on, Pn minus 1. Each process has a critical section, segment of code. Process may be changing common variables, updating table, writing files, etc. Like that, there are some process and these processes are changing its common variables, right? For example, if you are updating a table, what are the updated values and what is the table name? If you are writing into a file, what is the file name and what are the contents you are writing the file? So there are different parameters are there. So generally, the process may change these common variables. When one process in critical section, no other may be in critical section, right? So we have discussed a doctor-patient example in the classroom. When the doctor is there, in his chamber, only one patient can allow. one patient can allow. The remaining patients can be outside. So there is the same similar thing we are going to discuss here. Doctor is your CPU. Doctor is your CPU. The different process are, we can say, the patients. So when one process is inside the critical section, that is one patient inside the doctor, so no other must be entered into the critical section, right? So critical section problem is to design a protocol to solve this. So no other process should enter into the CPU, that we have to design. So each process must ask permission to enter critical section in entry section. So in the entry section itself, they have to take a permission. May follow critical section with exit section and remainder section. Now let us see this. See, when your process wants to enter into the critical section, this is the process. So do while loop, it is for maintaining the do while loop, while true. The process may enter into the entry section, there it will take some token, then it will enter into the critical section. Then after completion of critical section, it will go to the exit section. Then whatever the remainder section is there, that will be completed. So this is one kind of solution to your critical section execution. So this is the algorithm for that critical section process. See, do while turn is equals to j, then it will enter into the critical section. And then it will complete that particular task and then exit section, remainder section, then it is going to out of your loop. Right? This is the algorithm. Right. Solution to the critical section problem. There are three solutions for the critical section problem. One is mutual execution, the second one is progress, and third one is bounded waiting. Right. So this we can discuss in these three in the deadlocks concept. Mutual execution is if a process PI is executing in its critical section, there is no other process can be executing in their critical section. That is what we have discussed in the example. If a doctor is treating one patient and no other patient can allow to enter into the doctor's chamber. That is, when a process is executed by the CPU, no other process will be allowed. That is mutual execution. Progress. If no process is executing in its critical section, that means CPU is not executing any process, there exists some process that wish to enter into the critical section, then the selection of the process will be enter the critical section. Next cannot be postponed indefinitely. So if we say simply, if the CPU is idle, then if a process is ready to execute its critical section, then it will be allowed to enter into the CPU, and that must be in a progressive way. That cannot be postponed. Whatever the waiting process is there, that can be given immediate critical section, and that cannot be postponed. That is what progress. Last one is bounded waiting. Bounded waiting must exist on the number of time that other processes are allowed to enter their critical section. After a process has made a request to enter its critical section and before that request is granted, that is bounded waiting. And it assumes that each process executes at a non-zero speed and no assumption concerning to relative speed of the end processes. Right? So these are the solutions to the critical section problem. In the next video, we will discuss about Peterson's solution. Thank you.